So hello and welcome to another online meeting for MTH218. So it's getting close to the exam now, and so I was going to look at revision as the main thrust for today. I don't plan to get through all of it just yet, but at least start talking in the conversation. So I want to look at the exam first and then just revise some of the, say, trickier topics in the subject as my basic plan. Addressing some questions people have along the way, and have you digress for questions people have got. So firstly, about your exam. So your exam is 6 questions, each 20 marks. There are several parts to them, sometimes quite independent, just like the assignments are, I guess, in that regard. The value of each question is indicated next to it in the main. So that gives you an idea of how much time to take, etc. And how much perhaps internet work you might need to show, all that sort of stuff. So please use it as a guide. So it's a 3-hour exam. You do have a 10-minute reading time as well. Although it's technically reading time, you can write in if you want to, but it's still a really good idea to read through the whole paper in advance, just to see what you're up for. So roughly speaking, there are 2 questions for each chapter. It's not quite true. So there's about 2.5 questions on chapter 3, and slightly less than 2 questions on chapter 1 and 2. So they're 3 parts of the subject. So there's a bias towards the end, essentially. So it's although it's technically a closed book exam, you are allowed a formula sheet, so a double-sided A4 piece of paper with anything you want to at all. This sheet can be typed, or it can be handwritten, or a bit of both. If you've got good reading, you can shrink things down, etc. So let me just show you. So on this Interact 2 site, and indeed embedded in your study guide, and hello, someone else has joined on, there's an example formula sheet. And so here it is on the screen. If you can read it from where you are, you're doing pretty well. So one option is to use this formula sheet just as is. You could do that, and there's a bit of white space. You could scribble a few things on extra notes for yourself on the side or in the margins. And so I've certainly seen people do that. I don't see what most people do. Most people's formula sheets get taken. You're allowed to take them home with you at the end of the day. It's what's supposed to happen. All the little invigilators know that, and I sometimes see them. But a lot of people do that. I certainly see other people who will print this out. Say a one-sided sheet, they shrink it, reduce it even further, and on the other side they will just write down other notes to themselves. So maybe a question type that they have more difficulty with than others, and they will write down the problem and an example solution just to give guidance for themselves. Or sometimes the way I've written it down on the formula sheet just doesn't really gel well with them, and they write in their own way. So I've certainly seen people write stuff in notes, and I go, well, that's the same as that, but obviously that's for their sake, and that's fine. So for the people here, have you thought about what are you going to do for your formula sheet for your exam at all? And what you're planning to do with yours? Yep. So as you're typing, you don't have to use this one at all. It's just an example. Yep. So you've done like lots of other people, so cut it up and written some other stuff in. That sounds good. Murray, can you hear me at all? Okay. So if you want to add something, you can. If not, it's okay. I just want to make sure that you're at least on board. So it's a good idea to think about what you need for it. So certainly you don't expect to memorize every single formula. There's lots of them, as you can see, and other things that people find tricky are certainly some of the curves and the surfaces we did earlier on in the subject, so the quadrics, and so having some help for that. So that's what I've got at the end of this example one, for instance. So what are ways that can help you for it? And again, you might need other things that you found useful to work them out. So please think about what you need there. Some other things that are really important in this subject as a whole, and you'll certainly see it in your final exam, is the idea of problem solving. we have seen a big series of problems at times. Like, for example, a lot of line integrals, vector line integrals, you've seen your last assignment, or a bunch of multiple integrals. And there's lots of methods available. You've got to work out which one is the most appropriate to pick at any point in time. And so that's sort of problem solving. And a key aspect is that strategy. What strategy are you going to pick for it? And although some of that's mentioned in this my example sheet, not all of it. And so you might want to put more of that onto the sheet as you see fit. But just some things to consider for it. So, in order to help you practice, there is a sample exam, and that's embedded into the study guide, essentially, or it's just part of the study guide for all intents and purposes. And there are solutions for it, and there are video solutions for lots of them as well. So have a go through those. I'll mention some of those questions during my little presentation today, but it's good to practice yourself. In addition to that, there are some groups of revision questions and some solutions. So one set from memory. So again, the link is available in the study guide if you need it. So just proof of concept. So if you go to the sample exam section, you can see, apart from all the questions here, at the top there are links to some revision questions and some answers for them as well. And so you can use those for extra practice as you need to. So the big question is, how similar is the sample exam revision questions, etc., to your paper? And they're a bit different. So they are not. So I guess you can be the judge of how easy or harder it is. They are different, and because they're different, I suspect that means that people might consider your exam a bit harder. But I guess you can be the judge. Difficulty is very much in the eye of the beholder. It's trying. So I've written all the assessment together, and so I'm conscious of the fact that we've done all the assignments. Obviously, you've done all the sort of assignments, and that's trying to set you up for that's the same sort of style questions I'm going to ask in your exam. An exam is a little different, that you have a little more time pressure, and so questions are tweaked slightly as a result of that. They've done their sort of catches at times. But just like in the assignments, you often get a batch of multiple integrals, or a bunch of flux integrals, a bunch of vector line integrals, whatever it might be, and you're going to have to work out what the appropriate method is. You'll get the same thing in your exam. And you can see that in the samples too, for that matter. And again, there's choices. So if you think through all the different methods, we've got to some of the things. I couldn't ask them all in an exam. There's just a few too many. And so there's going to be some choices there. And so some of the methods that are not in the sample exam might be in your final, and vice versa. Just beware of that. So you can't study just those alone and hope that's going to be everything. Probably be enough to prepare for a pass, no, well and truly, or maybe even a higher grade. But have the big picture in mind. And certainly the assignments have been going about trying to assess everything except perhaps the flux integrals, which is why that optional question on assignment 3 is there to help you prepare for some of the vector calculus questions. Maybe not harder, but just extra questions at the end. So question 6 on your final exam. So that's some information. I have put more other information in the exam guidance statement on the Interact 2 site, but it's similar to what I've elaborated just now. So next thing is about, well, let's actually do some revision. So in terms of questions, so I think in last year's exam, to give you an idea, the questions that people found the hardest was a question on quartics, so quartic surfaces, another one on a triple integral question. They had to be the hardest. So in other years gone by, some of the harder questions, the ones been involved curl and so the Stoke's theorem, so curls and divergence theorem have also been some of the harder questions that people have encountered. It changes as people change and as the questions change, but there's some of the harder ones. So that's some of the things I want to focus on, as well as some other questions people have raised. So first thing, certainly in topic 1, we did partial derivatives, which most people are fairly okay with. Certainly, if you manage to get this part of the subject, then you're okay with them normally. But you've got to remember you do tangent planes and differentials, and steepest and direction of steepest descent, slope of steepest descent, direction of derivatives. We did lots of those sorts of things. But that's really part of the calculus aspect. But the thing that I suspect that people really found difficult is normally the drawing stuff, particularly when it comes to the quartics or things that are in high dimensions. So I've just got one harder question here. So just reminding some of the different aspects that you need to do. So I've got a function of 3 different variables, which is code for all that. Boy, that's hard to try to visualize. And because it's hard to visualize, let's just try to reduce the dimension. So in order to try to draw it, you have to do 4 dimensions, I guess. So if you just drop a dimension down by considering level surfaces, so you're just going to fix it for different FAs. And I've got 3. So again, how I'd ask these sort of things in the exam is, instead of saying find all the level surfaces, which is how questions are in an assignment, I might narrow it down just to fix on 3 or 2 or whatever it might be. Just to make it really clear, easier to mark and easier to do in a constrained amount of time as well. Sorry, just my other pen in my hand. So in this case, I got this level surface. I would like to fix it for a certain value. Let's call it f for the moment, and there's 3 different values. And I would like to try to work out what particular surfaces is. And there, as you can see, all the terms here are quadratic or less, and therefore it's going to, when you rearrange, it's going to give you a quadric surface. So the first thing to do is probably just to standardize it, make it look closer to on the standard forms. And so to that end, just clear the fraction. Is the first bit. Expand out, and you can see there's quadratic terms for x's and y's, so I chuck them together. So the x squared minus fy squared. I've got a constant term which you could put anywhere I want to at all, so I'll just put it over here. So, and then I've got a linear term z, and to get in closer to the standard form, I'm going to make it z is equal to all of this sort of stuff. That's not the only way of writing it down, but certainly clearing the fractions is probably the most critical thing to do. So now I've got this sort of format. I could sub the f values in and do them all separately, which is fine. But what I want to do is I want to try to work out what each particular surface is. So they're all quadric surfaces. And so the basic strategy to work at any of them is to do traces. So sometimes the standard form helps, and you can compare that sort of format to what's in your formula sheet, and that often give you an indication, which is fine. And so that's the standard format for a blah blah. But traces is a good way of doing it. So basically what I'm going to do is fixing the values for different values. So I'm going to fix the x's to begin with. So if I fix x's, essentially, what am I going to get? So if x is fixed, that's just a constant number at the front here. So y is equal, so z is equal to a constant with a y squared term. Well, that's just a parabola. So when I've got a mix of a linear and a quadratic term, I'm going to get parabolas cropping up. If I fix y, same sort of thing happens. So again, the y is fixed, so it's z is equal to constant plus x squared. That's a quadratic term, so you get a parabola. And you can do a few things. So since it's positive x squared, it's going to be a parabola facing up. For x is fixed. Depends what f is. So if f is positive, or if is 0, or if it's 0, you get different sort of things happening. So when x is fixed, if f is positive, you're going to up to down. Positive, it's negative, it's smiley face. If f equals 0, that's not quite true. That's sort of a separate case. You're getting a sort of constant happening. So which is saying z is equal to a point, effectively, which we'll have to come back to later. So the last one we've got is z is fixed. So when z is fixed, so we've got a constant is equal to something with x squared minus fy squared. So we've only got the quadratic terms. So we've got two options. If f is positive, we're getting a sum of squares. And so when you get a sum of squares, they end up being ellipses, or more precisely in this case, it ends up being ellipses in general, I should say. They can be circles, but in general ellipses. If f is negative, that's not true. Let me say this properly. If f is negative, then you're getting sum of squares, which is ellipses. If f is positive, then you get a difference of two squares, which gives hyperbolas. So why I picked this example over everything else, so a slightly harder one, admittedly, is that I've got all three, parabola, ellipses, and hyperbolas, all cropping up in the first context. So that's why I picked this one. So all of them three prop up. So parabola is a mix of linear and quadratic. Ellipses is a sum of squares. Hyperbolas is a difference of squares. That's the basic way of detecting them. So when you do traces, so f equals 0 is special. So we'll leave that one to one side for the moment. But if for the other cases, so f equals minus 1 equals 4, you got traces in two different directions being the same. That gives you the basic type. So for f equals minus 1 and f equals 4, both of them would be paraboloids, because we have traces in two different directions being the same. Then to work out what type of that is, you look at the other direction. So in this case, z's the last direction. And so if f is negative, like f equals minus 1, you're going to get a elliptical paraboloid, or actually more correctly a circular paraboloid in this particular case, if you think about it, but elliptical's fine. If f is positive, the other traces are hyperbolas, so we're going to a hyperbolic paraboloid. So that's the way of working out quadric surfaces. The last one we haven't really considered, f equals 0, that's the special case. It's worthwhile just writing it out again. So pretty much you're getting z is equal to x squared is what it reduces down to. And that, you notice there is no y terms there at all. So when you reduce down to just reducing one, if you drop a variable, it ends up getting what's called a cylinder, and each of these cross sections will let just a parabola. So this is called a parabolic cylinder. Sort of how you'd work that one out. So that's how you work out all the different types of surfaces. I'm just classifying it. Let's try drawing them. Okay, so to draw them, we sort of need to anchor them down a bit. So what would be really useful is to work out the center for certainly these two, just to help bend them down. So you've got elliptical paraboloid. So that's when this here is f equals minus 1. So pretty much you'd normally so you complete the square in a really hard question. In this case, they're already completed. So when the x squared and y squared is 0, that vanishes. You can see that z is equal to minus f. And so x and y being 0 is fine, and then otherwise z is equal to minus f, or 1 in this case, will give you the centre. In this case, it's a paraboloid, so it's going to be the elliptical paraboloid, so that'd just be the stationary point for it. And otherwise, for f equals 4, it's 0, 0, minus 4. And that would be the saddle point of the elliptical paraboloid. So then we have to try to draw them. So I get x, y, z. Let's try to draw all of them in the same sort of axes. Now I do tricks, if you remember, of sometimes shifting the axes that are not at the origin. You can do the same thing here, and again that doesn't go straight in this case, so I'm just going to leave it as it is. So for f equals minus 1, it's an elliptical paraboloid, so you can pull out your formula sheet and you go, oh no, that looks like either a hill or an upside down hill, a big bowl. If you look carefully, it'd be for f equals minus 1, z equals positive x squared, positive y squared. That means it's just pointing up normally. And so we're going to get a nice sort of bowl shape around about above the center, which is 0, 0, 1. And otherwise, the cross sections are ellipses, or if you look carefully, end up being circles. So what I'm looking for when I'm marking this sort of thing in your exam is your ability to pin it down into space. So in this case, give the vertex and be able to give the orientation right. It's pointing in the direction of the positive z-axis. So they're the key things in terms of putting it down. Otherwise, it's supposed to look vaguely like an elliptical paraboloid. So you've got to get the basic shape, location, and orientation of the three things I'm looking for. So for f equals 0, it's a parabolic cylinder. So I'm just going to ignore the y value for a moment. Otherwise, z equals x squared is just a parabola, which looks something like that. That's a parabola. And it's the same for all z directions. So that's sort of the idea. So it's a big trough, essentially, extending in in both directions. So just a really big, giant trough is the idea. Hard to draw, and passes to the origin. That's the z equals x squared bit. The last one of f equals 4 was a hyperbolic paraboloid, which basically looks like a saddle. That's the sort of classic saddle point. And again, you can look up your formula sheet to what it looks like. So the saddle point is at minus 4, and then you have to work. Then it's worthwhile just having a look. So if f equals, so in the y direction, so fixed y values, looks like a smiley face. So for fixed y's, you're going to get a sort of curve in that direction, and for fixed x's, it's going to curve the other direction. So for fixed x's, when it's positive, you're going to upside down. So that's the sort of idea of the saddle point, and it's a pretty bad drawing, but that's the idea. So 0, 0, minus 4 is the key point. It goes the other way. So if you look at maybe better drawn picture from the formula sheet, you can sort of copy down. what you're trying to draw is this sort of shape here. And so what I just did then is basically draw the curve in one direction and the other direction. So that's what I drew essentially, those two, the key points there. And so to give it a bit more shape, drawing a few other bits of the saddle might have been useful. Makes it worse, I think, that last bit. So, as you can see, I find it difficult to draw some of these things too, and so you're going to be marked generously with these things. You're still going to have to hand draw them. But as you can see, I'm looking for a basic shape, so you're supposed to know, hyperbola is supposed to look like something like a saddle, and just trying to draw that. Otherwise, fix it in space and getting the orientation right. So getting the X and Y values around the right way, sort of thing. And you can see in this case, at first glance, the level surfaces look quite different, depending if they're negative, 0, or positive. They're quite extreme sort of differences for it all. But there's a continuity between them all. So essentially, as time goes on, the Y direction opens up, becomes flat, you can see, and then starts curling around. So that's a revision about quadric surfaces, and I said, certainly last year that was a question that people found difficult. So I hope you can get through it. Other sort of questions was double and triple integrals. So people don't find this so difficult, but I want to mention it. Sort of the next big chapter in chapter 2 we spent some time on. Basically, the thing I want to focus on is the strategy. So instead of doing any heaps of practice questions, I just want to focus on the strategy. So here's some questions down the bottom here. So first strategy is, for a double integral, work out the region of integration. For a triple integral, again, try to draw the region of integration. For a triple integral, it's easiest understood as a three-dimensional solid. The 3D sometimes gets a bit tricky to draw. So if you can't do that, at least draw the base. So if it's sitting in the XY plane, draw the base. If it's sitting above it, draw the shadow it casts on the XY plane, or effectively the projection of the surface down on the XY plane. So that's what you should be aiming to draw. And that's the key thing. Once you've drawn the region of integration, sometimes that tells you what to do. So from looking at that, you can say, oh, it's a bit of a circle. That should tell you should do polar coordinates. Otherwise, you might be a type 1 or a type 2 region. Again, that would suggest how to do as an integrated integral. Or you might notice it's both, so you go, I know I've got the flexibility to do it either way as I see fit. So once you do that, change the polar coordinates as appropriate, but otherwise, pretty much do it as an iterated integral from whatever type. So if it's type 1, integrate the y's first. If it's type 2, integrate the x's first, as the case may be. So do the iterated integral. Sometimes when you do that, you get stuck. So be prepared to realize that, no, this is actually getting hard. I need to do something else. So a backup option is, if it's not working, is try reversing the region integration. And that's a possible outcome if it's both a type 1 and a type 2 region. So you can do both at the same time. Another choice that you can do, which in this subject in your exam will be told to you quite clearly if you have to do that, and that's use a change of variable. So it would mention the question, this is the change of variable, do it by this method effectively. So at least that one is you'd have to think about it, but you still have to do it. So that's the basic plan of attack. So let's copy these 3 examples down. So instead of, I don't want to do them all the questions, but I just want to look at how you work out which method to do. And as I said, I think a good idea is to draw the picture. So this first one is a rectangle. The x-coordinate goes from x equals 0 to x equals 2, and the y value goes from -1 to 1. So I'm integrating this particular region. Now, being a rectangle, it's both type 1 and type 2, so I could pick either way I wanted to. And so you can go, well, I can integrate either one I want to. Looking at the integrand, they pretty much both have x's and y's at the same sort of level, so it will make no difference which one you pick. So you just do this one as a straight iterated integral, and you're fine. So for the next one, you have to try to draw this region. Can someone tell me what type of region that is? So let's have a look. So still like to know. So x is greater equal 0. So that means we're on this side of the y-axis. Y greater equal 0 means you're above the y-axis. So it means we're only in the first quadrant. That's what the first two tell us. Yep. And otherwise, this one here tells you it's a circle of radius 2. So cheers. Now, as soon as you go, oh, that's a circle, that tells you that polar coordinates are going to be a really effective way of doing it. And then, as polar coordinates, dA would become dr d theta, x become cos theta, y would be sine theta, just writing what polar coordinates are, and then the limits for r, because it's just a bit of a circle, would be from nothing up to a radius of 2, and theta, because it's just the first quadrant, would be from 0 up to pi on 2. And once you have that information, then you basically transform this integral into polar coordinates, effectively integrating over a rectangle then, so it's transforming from a bit of a circle to a bit of a rectangle, and then otherwise do as the integrated integral. When you look at these terms here, you get r cos and r sine, you could separate it out and go that way if you wanted to, so again, it doesn't make much difference after that. But realizing it's polar coordinates is really important, and drawing the picture, as I said, helps you work out, say, the limits for theta in particular. Because you can see the limit for radius here, the biggest radius is 2 squared, but you might find it harder to see what the limits are for theta without drawing it, so it's important to do. For this last case here, as I said, although it's written as an integrated integral, I still would draw the picture first. I still think it's useful. And so the inner limits are x's, so we've got the inner limit is x equals 3y, and x equals 3. So x equals 3 looks something like a straighter line than that, 3. And x equals 3y is this line here, so x equals 3y. So when y equals 1, x equals 3, and that's supposed to be a straight line. Let's have a bit another go at it. Okay, that's 1 over here now. So that's the two bounding curves here, and then we know that y is from 0 up to 1, which is the whole region. So what we're trying to do then is integrating over this particular triangle, essentially. So it's good to know that. And because it's a triangle like that, it's both a type 1 and a type 2 region. And so seeing that picture knows, well, you can swap the order integration if we need to. That's an option available to us. But otherwise, we just try as directed. And so you just go, well, please integrate it as written, try to integrate e to the x squared, and you go, hold on a sec, I don't know that one. And nor do I know any tricks, like there's not a really product there, so I can't really use product rule. And again, there's a function of a function, so substitution might be a good idea, but if you make a substitution of x squared, there's no way of recovering the x anywhere, it's just going to get messier. So that doesn't really seem like an integral that I know how to do, so swapping order integration sounds like a good option. And seeing the picture helps you know that at least that is a possibility. So that's a good idea in this case. And so swapping order and integration, basically you have to consider it slicing it in a different way. And so this top curve is y equals x on 3. The bottom is y equals 0. And you can see you go from x equals 0 to x equals 3. And so the limits now become 0 to x on 3 over e to the x squared dy. And then you're getting x, and the x is go from 0 to 3. Then if you do that integral, this inside one is easier because it's got no y's in it. So the integral becomes much more straightforward. And when you do that, subbing the limits, you get the x, which is what you really need to do integration by substitution in an easier way for it. And doing the reversing integrals makes the problem fall out nicely. So that's the basic idea of strategy. So again, leave the rest of the exercise, but that's the sort of ideas you need to look for. Okay. So that's the idea for strategies for multiple integrals. So that's sort of end of part 2. You can see there's a bit in that. And then the last topic we've done is vector calculus, which we've done lots of things. So I guess the two main ways of talking about it is in terms of line integrals and surface integrals. So the sort of two main things we've done, with some very important peripherals around it, like divergence and convergence, etc. And divergence and curl, I should be saying. So what about line integrals? So this is a question that someone in particular asked. So you've got lots of methods available for vector or line integrals. Which ones do you pick? So again, this is my idea of the strategy. This is my version of it. So if you've got a vector line integral around a closed loop, then and it's in 3D, use Stoke's theorem. If it's a vector line integral and a closed loop in 2D, use Green's theorem. That's what I would do. Maybe I should have a step before this, and that is if it's a scalar line integral, which normally are really clear. So for a scalar line integral, so we get a scalar line int, which pretty much means there's a ds there. So if you get the ds, then you pretty much need to parameterize. You can see that straight away. I mentioned it down the bottom here, but that would be the first thing. So as soon as you see the ds, you go, bang, that's a scalar one, I'll just parameterize it. So if it's a vector one and it's closed, use Stokes for 3D, Green's for 2D. Otherwise, you like to try to have some help. And so the next thing actually you do is we try to check if it's a conservative field. So do my necessary checks to see if it's conservative or not. So in a 2D, I just check if I'm doing the partial derivatives of the opposite order gives you 0, fantastic. In more general, if the curl is 0, that tells you it's conservative. If you do know it's conservative, that means you can use a fundamental theorem of line integrals, which is great, which means you can just work out the potential function and sub that in and you've got the answer. Or you can use path independence to give you a nicer path to integrate along. So that helps. Although it's a little bit of effort to checking, it's a worthwhile sort of thing to do. If it's not closed and it's not conservative, then you try to do some tricks of, well, is it a length of a straight line or a bit of a circle? That sometimes helps. That's limited, and if all else fails, then you'll have to parameterize it. And you're avoiding that where you can. You can do tricky things, like I mentioned something like this akin to Stoke's theorem last week, and that is if you've got an open curve somewhere, you can make up another curve, which is easier. So like all straight lines, for example. Let's see if it lets me draw it though. Yeah. So you can get a closed off curve by something a bit easier, like two straight lines. And when you close off the curve, you get a closed curve in that case. So you can use Green's theorem for the closed bit. And so the closed region you can work out by using Green's theorem. The bit of the straight parts hopefully is easy. You could do by straight parameterisation in a straightforward way. And then the harder curve you could then do by difference. So that's an advanced technique which you sometimes you could use in an exam potentially. If I've ever asked a question like that, that would not be the only way of doing it. But that's an idea. So that's a basic strategy. I'll show what I mean by some of these in a second. A question people had on this too is that I often use the word traverse when it comes to vector line integrals. And what does that actually mean? In general English, it sort of means the idea of to walk or scale. It means to go, literally means to travel across, essentially. So, what I really mean it for in this subject is the idea of moving along a directed path. And normally I use it to indicate the direction of the path, essentially. So a line integral has to be an integral along a particular path, and the direction is important for vector line integral. And so when I use say traverse, I'm just trying to say that's the direction that you're walking along effectively. So if it's a surface, which way do you walk along? Forwards or backwards? So in this case, here's the word traverse in the second last example. So I've got a vector line integral. I've got t as the boundary of a triangle with certain vertices. And you go, well, I've got two ways. I can walk around clockwise or anti-clockwise, essentially. And so to determine the order that the path is, or the direction the path is in, I use the word traverse, or traverse in this case, to indicate the direction that it's been covered in. So in that order that's been given. So that's just a bit about traverse. So let's just quickly do strategies for each of these. Again, I won't do the calculations unless you want me to, of course. So I might just do the last one since I haven't done another example similar to it. Okay, so you've got various functions. So this first vector line integral has a vector field of a parabola and it's open. So it's an open curve. So Green and Stokes automatically get ruled out. So well, I'm trying to save them some work, and so I could try to take the try to see if it's conservative. And to work out it's conservative, if you give them in 2D, if you call them P and Q, then you just do the opposite derivatives, so Qx minus Py. If you do that sort of expression, if that's 0, bang, it's conservative. So you could try checking it out. And in this case, you do get it actually equal to 0. In that case, bang, fantastic, it is conservative, and that means you can use the fundamental theorem of line integrals, so you can work out the potential function. And so if you integrate P with respect to x and keep going, you can work out what it is, and just by looking at it, it's going to be minus cos xy, I think, would be the potential function, plus c if you want to put it that way. So there's more work to it than that, but as soon as you check, first you check this, there's some work to it, of course, and you realize, oh, that's 0, bang, I know it's conservative, I can use a high-level theorem, a fundamental theorem of line integrals to help me out. Okay, that's great. So for the next one, I'm integrating where the C1 is the right-hand side of the unit circle, staying at 0, 1. So that particular curve just there. And it's an open curve, and being an open curve, you can't what was I saying? So being an open curve, you can't use Green's theorem, well, not directly at least. Then you could try this Qx minus Py to see if it's conservative or not, and you're going to get getting minus 2, which is non-zero. So therefore it's not conservative. So you really have to fall back to trying to go, well, can I do other tricks? It is a bit of a circle at least. And the answer is, well, it's still not something straightforward. And so at first glance you go, okay, well, I could just resort back down to parameterisation. You can do some tricks as well. So this vector field, so this is the geometric trick. The vector field is always perpendicular to it all, which means it's going to add to it. So if it was the vector field is always parallel to the path. If it was perpendicular, it'd be 0, easy. Since it's actually parallel, you actually have to practice have to do details. So you're really going to have to parameterize this one, unless you want to do some advanced stuff. So the advanced thing is to close it off along the straight line, use Green's theorem for the circle a bit, and then a separate part. I'm not sure if that really would save you much effort though, in all honesty. So just parameterizing probably is going to be the quickest way in that case. Now the next one here, you notice it's actually got 3 dimensions. That's the first thing. So we're drawing a vector line equal the boundary of a triangle with vertices. Because we're traversing a closed region, it's a closed curve. So Green's or Stokes would be a good idea. And in particular, because it's 3D, Stokes would be the way to try it out. So Stokes' theorem requires you to work out the curl of this and then integrate the curl over the enclosed region of the triangle. Would be the way to do it. But that's recognizing that Stokes is important in the first place. This next example is the same thing, but it's over in 2D. And so you're going to use Green's. So integrating a closed curve in 2D, Green's theorem is going to be useful. So that's how you recognize that one. For this last case, it's a DS, which basically means it's a scalar line integral instead. So you're trying to work out you're just adding up the x values along the whole arc length. So you'd use this sort of calculation to work out, so the average x value along the curve. I'll do this one just to show you how to do it. So you really are forced to do parameterizations for these sort of questions. And so you need to work out derivatives, essentially. So x dash is 1, y dash is 2t, z dash is 2t squared. Now, we've got a differential of ds here. So the differential ds is pretty much the length of the vector containing all the different derivatives. And I've got 3 of them here. So the length would be, so the square root of the sum of the square. So it'd be 1 squared plus 2t squared plus 2t squared all squared. So if it was in 2 dimensions, you just sum up the square of the 2 derivatives. If it's 3 dimensions like I've got here, sum of all 3 squared and keep going. So that dt. And again, it'd be nice to try to simplify it down. So it's 1 plus 4t squared plus 4t to the 4. It's square root, hopefully, and what you're really hoping for in these cases is that the square root disappears. That's the nicest scenario. And if you notice, that's a perfect square underneath, so that's 1 plus 2t squared all squared underneath. And so you're getting 1 plus 2t squared dt as our sort of final expression, which is nice. And so our integral x ds becomes the integral for t from 0 to 1 of x, which is t, times by our differential, which is 1 plus 2t squared dt. And now it's just a simple integral. You have to expand the brackets really, expand the product, and then integrate as per normal to get your answer. But I just wanted to sort of show you that. So I have only done examples when we've done scalar integrals with 2D. Just want to show the 3D case. Fairly similar, but it's could just see what it actually looks like. So that's some vision. So I will leave it there in terms of introducing more content. But I did have a question that someone wanted me to look at, so I'll do that now. So what I'll talk about next week is more about the strategies for flux integrals in general. But I will just do the main question that someone asked, and that was looking at sheet 10. 4 and 5. Okay. So this is a question people asked, and I'm running out of time, so I can do some revision next week. That's okay. But this one says use Stoke's theorem to work out this particular integral. So this is a flux integral where the vector field present is actually a curl. So when you do a flux integral when the curl is present, then that is a term or phrase you see in Stoke's theorem. So that would, so as soon as I see that sort of term, I'm thinking maybe Stoke's theorem is a good way of doing it. So what Stoke's theorem states is if you're doing a flux integral of an open curve of a curl, then the this is equal to the vector line integral around the boundary of that surface. That's what Stoke's theorem states. So as soon as that, you go, well, maybe I should try Stoke's theorem without looking at anything else. So as long as I can work what the boundary is, then that's a good way of doing it. So if you look at this picture here, the surface is a hemisphere, so it means it's a half a sphere, so that sort of thing. And so the boundary of the curve, the boundary of the surface, which is what I need to know, would be just this curve here, which would be when z equals 0, so x squared plus y squared equals 4. So I'll just sub in z equals 0 into that essentially, and z equals 0. That's my boundary curve. So on this curve, what's f dash going to be? So if you look at this curve, it's complicated, it's got lots of terms, but you notice that there's lots of z terms. So you've got when z equals 0, the first term just becomes x squared. Okay, it's nicer. Next term again, e to the 0 disappears, so you're getting y squared j. And the last term here just disappears, so it's 0k. And so on this curve, the vector field simplifies down greatly, which is nice because that means that you've got a chance of doing it, because that looks pretty nasty as written. So although you could work out the curl, trying to do it directly as written would have been difficult. So what you really need to do to work this one out is you needed to change the region integrating over. So either you needed to change it to just a curve, like what I'm doing here, or you could use Stoke's theorem twice to integrate it over a different surface which has the same boundary. So you could have done the same integral just integrating over the disk. The flat disk would also be okay. So this is what the function, the vector field looks like on that curve, and so the integral will basically become integral around this sort of circle of x squared dx plus y squared dy, and plus no dz if you want to think about it. So that becomes the simplified curve. This is integrating around a closed curve, effectively just in the xy plane, and so you could do it by parameterisation, but I would be thinking that maybe Green's theorem might actually be helpful at a point in time. And if you do Green's theorem, I think the answer is going to be 0 in the end, because it's actually, when you reduce it down to this, you're getting a conservative vector field. So this is now, as written, this is conservative, and so you get 0 as the final answer. So what did I do there? As I said, the first thing I noticed, I thought, bang, that just reeks of Stoke's theorem. Let's just try it out. That seems the obvious thing to try. And when you do that, you see that on the boundary at least, the vector field simplifies down to something much more workable. So as long as you stick with that one, it becomes workable. And because that new vector field, at least for that sort of domain we're considering, or the boundary curve, it's conservative, then you can get much easier to work with. So that's the way I would try to do that. So as you can see, using those powerful theorems help you basically move integrals over some complicated objects into simplified ones. So either you can, as I said, you either just converting an integral over the complicated surface just to its boundary, or what I'm doing by using Green's theorem, effectively, is I'm changing it to integrating over a nicer surface, namely a flat disk, rather than the whole hemisphere at the top. That's what the Green's theorem approach is using. And you can see when I've used Green's theorem down the bottom here, I'm using the new functions I've got rather than my original ones. And I can do that because that's what it simplifies down to in this particular case. So if you have any questions, ask, but because it was one of your questions. Yep, so I'll just do the other B and I'll come back to the same thing. So the same sort of question, you've still got the same idea. So you've got a box consists of the top and 4 sides, not the bottom of a certain cube. Which is much easier. You know what, I should have just drawn the axes in last, I think. So the axes sort of pop up through the middle of the box. So it's a box, but it's open. So the bottom here of our big box here is open to the wind. And so you've got, again, an open boundary. And so instead of trying to integrate the whole flux over all the blue surface, you can just use Stoke's theorem to work it around the bottom curve. And when you do integrate along the bottom curve, this is all when z equals -1. Again, you can plug that into the various terms here, and that makes the vector line integral a bit easier to work with. And then you could apply Stoke's theorem a second time to just integrate of the curl over that particular region, and then that's -1. So and then you can just put the curl of the simplified version of f in that case. So you still have to use Stoke's twice, is how I would think to do it at least, because integrating over a square looks pretty nice rather than 4 individual pieces. So again, that's big picture. I can do more details if you want to. Yep. So there's some ideas. So as I said, using the big theorems is a really good way of trying to do it. So you can sort of use Stokes and Greens to that in that particular case. Now, Murray, you said you have a question too, so I'm happy to look at yours. Just waiting for you to type in. It's hard to type in. Yep. Yep. You've got microphone, right? So you'll have to just click on the little button towards the top of the screen to turn it on, I think.
I can hear.
Yep, I can hear.
So on the study guide page 191 gives a comparison between three forms of vector surface integrals.
Yep. So it's three forms of, yeah, you just dropped out there, I think.
Right, so the line integrals are double integral, and then the flux integrals are single integral. And I've got my head fully around the line integrals now with the dr, ds, and the dx, dy. And then just getting my head around the new flux integrals. But in tutorial 9, in 9.9 and 9.10, you've then got flux integrals which are written as a double integral with dA, which can't really see how the method is done in the answers, but I'm struggling to see where that fits in with the other notation for flux integrals. Whether there's some relation between the dA and the ds, or whether it's...
Yeah, this is my sloppiness notation partly. So a line integral is integrating over over something one-dimensional. So it's just it's a single differential. So as one of the examples you just said then, so it's x squared dx plus y squared dy is a vector line integral, and you can see you've got single differentials there. And although we write that down in compact form using dot product, so dot dr or something like that, and that's what a vector line integral is. So for flux, they're integrating a function over a bit of area. And so you can say it different ways. So essentially, it's a bit of area, so I sometimes write as dA. Now, I want to give a sense that, so if I just write FDA, so this is how I write it down on a piece of paper. I'm writing down on screen. So when I write down DA, if it's just a normal letter, so normal typeface, that means I'm referring it to just a simple double integral over a flat piece, essentially. So it's just a flat plane. So DA would be a small bit of plane. And that really is just a double integral. To do flux, though, I really want to consider how a particular vector function is passing through a particular direction of a piece of area. And so I can write it in either way. So these are the synonyms for each other. So these two are the same. So the confusion is because most of the time I use this notation, but it's actually the same as the top. So I sometimes use the top. So what does this really mean? So this is code for saying I'm really adding up the component of my vector field in the direction of the normal, and I'm adding that up over the entire surface area. And so I write down, say, ds here to indicate the whole surface area. And I could say A for area, and that's what it is, just adding up bits of area. But just to give a sense that often they can be curved, and therefore we have to do other sorts of different ways of handling it, I write down ds to indicate that sort of curved surface area, so S for more curved surface area. Where dA, I normally, but you can see I'm slightly sloppy sometimes, I try to refer to just dA as simply being a flat area, and so therefore can be resolved to say dx dy, but ds is a bit more complicated, you have to do some fancier stuff with. So that's a distinction. So as I said, I think the real problem is just probably me, the fact that sometimes instead of saying S, bold S, to indicate a directed and a bit of an area of a curved surface with a direction, sometimes I'll use the letter A A for area rather than S for surface area. So I'm not sure if that clears it up or not.
Somewhat. I'm happy to know that they're the same thing, basically. But then I've got an issue where in the answers to tutorial 9.9, it requires just a regular normal vector, whereas previously the other Flux questions I had to find the unit normal vector. I thought that was the difference between A and S, but now I don't know.
Okay, so yeah, so I'm just looking at the answers. Okay, so to work out, so I guess this is true. So therefore, to work out any sort of flux integral, you're basically working out the component of the vector field in the direction of the unit normal, so a little n for unit normal, and adding up over the whole surface area. Now, if you're adding up over the surface area, if the surface area is a nice flat region, like a bit of a plane, then that just really can be thought of as just a bit of, this can be written down something like dx dy if it's a bit of a plane. And you go, fantastic, just a normal double integral, I can do it straight away. But if it's actually genuinely a curve, you can't do that. You have to do something different. And so just like when we had the little ds before, the S in that case stood for arc length. It's a terrible letter probably, but anyway, that's the little ds that he did for the arc length. This is for a vector line integral. I had to introduce effectively the length of the tangent dt, so I had to, and which would end up being in our case the square root of x dash squared plus y dash squared plus z squared, to actually transpose it into just a simple letter. And the same sort of thing here is that in order to change this into just a nice flat region, I'm going to, I still got f dot n, so I still got that component there, but the ds ends up becoming the length of some particular vector here, that we'll work out in a second, times by the normal flat area, so I might say dx dy. So this ds here, because it's curved part, you actually have to add a term at the front here to capture that curved part. So, and why? I mean, why is the case? So if you've got a bit of square here, the area of this, it's got length dx and dy as the two different lengths, then the area is just the product dx dy. That sort of makes sense. But if it's a curved region like that, even though the length of the individual parts might be, dx dy, that sort of idea, because it's curved, because they may not look like a rectangle from above, like it could look like some other sorts of shape, it could be a bit bigger or a bit smaller, and so we need to introduce other sort of term in here to capture how curved it is, and that's called the length of n. And so what ends up being easier is if you just bring these two terms together, the unit normal and this particular length thing together, as just saying that's f dot capital N times by, say, dx dy, or in terms of the key parameters. So in practice, what you really do is you have to parameterize the surface. So x and y are the obvious ones, so they're the Cartesian coordinates. They're not the only ones you have to do, but in most cases that we'll consider in subject the ones to pick for. So you basically parameterize the surface in terms of two coordinates, and then you work out what n is in that particular coordinate system. If it is Cartesian coordinates, then capital N is end up being plus or minus, depends, minus zxy, minus zy, 1. And where that thing came from is looking at, well, this bit of curved surface, what are the tangential directions in that particular case, knowing what the tangents are, you can do the cross product of the two to work out the area of this particular region, and it gives you that sort of thing cropping up essentially. Very vaguely where it comes from. So that's that's why that one. So the reason why we have to do this different case, we have to use this capital N rather than little n, is because it's a curved surface. So if you go back to sheet 9, question 9.
Capital N was just a regular normal vector, and the smaller n was a unit normal vector.
So capital N it's not just any old one, it is a particular formula for it. So these are the formulas. This is the formula sheet, so it's easy to maybe pick it up from there. So it's actually that particular vector there. So it's a special one. It's the cross product of things. What it ends up reducing down to in Cartesian coordinates is that one there. So it's just that very precise form. So it's not a unit vector, which is why I don't use little n, but it's a particular normal vector, nevertheless, which has special properties that are useful for us. Is that any better? I don't know. So you're right, little n is the unit normal vector. Capital N is another normal vector, but doesn't have to have length of 1. But the length of it has been chosen in a special way to cater for the curvature. So as I said, this ds, when I write it down properly, is trying to say that's a curved surface area of curved surface. dA is interior area of a flat bit of surface, which tends to be an easier thing to do. That's the differentiation I try to use, but as I said, I'm a bit sloppy, but sometimes I interchange them.
There's also the A that's...
Yeah, if it's an A bolded, it's just the same as really saying this one up here, which is the real confusion, I'm sure. So if you got bold, anything to do with bold suggests it has a direction attached to it. And so when you're trying to work out flux, you're trying to work out flux through in the direction of the surface. And that's where the bold nature is.
So I've got a note here that I've made from the study guide that that ds with s being bold is equal to the unit vector with ds that is not bold.
Yep, that's right. Yep.
So if I just change the s's for bold A and then d with dA with bold A, and then unit normal vector with a dA which is just a standard dA, that would be the same thing, right? Because then I'm just changing the s's for A's, one bold and the other not.
Yeah, so that's true. It's still about working out what the region of integration is. So study guide here. So in this question, so if you look at the actual surfaces you've got here, right? So this is the surface z equals minus y plus 1. So this is a plane. So it's still a plane, but it's a plane not parallel to the xy plane, but it's going to be a curve to it. So it's going to be at a 45-degree slope essentially. Is what the sort of plane it's going to look like. And so when you're trying to work out the dA in that case, instead of when you're looking at it from above, it's not just a square or whatever it might be, but it's got a slope to it, and you have to multiply by a certain term to fix that up. And so one way is just to go, okay, well, I've got the flux of my thing dot ds. I mean, I certainly can write it that way. And you go, well, I know that's going to be f dot n times by a bit of surface area. I still can do that sort of stuff. But the problem is this surface area here is not going to be simply dx dy, or in this case, not going to be dx dy, but rather it's going to be dx dy times by some factor just to help work it out. And that factor that you need to work out in this case is the length of n, shall we call it, dx dy, and the formula for the length of n, if you want to take this approach, is it's the square root of partial derivative with respect to x squared plus the partial derivative with respect to y squared plus 1. And so in this case, it's z is equal to minus y plus 1. And so this correction factor, if you want to call it that, that's going to be 0, that's going to be 1, so you'll get a correction factor of root 2, because it's a nice plane, it simplifies down. So you still could work out the unit normal like you would normally. When it's a plane, you could read it off even, because it's a plane. And then you still need to work out the correction factor. So you can do it that way. So you work out the unit normal yourself, and then work out this correction factor, which here it is here separately. But often if you have to go this approach, it ends up easier to do them both together, is my feeling. So I mean, another word here is that doing these questions, I would try to use high-level theorems wherever I could. So I would actually try not to do these calculations if I really could help it. Sometimes you have to. And so looking at this one here, not much of a choice really. So for the second one here, which is paraboloid, I would try to use the divergence theorem here indirectly is how I think to do that one, for example, looking at them. Just because I really hate doing that approach. But anyway.
The tutorial questions is they're asking two integrals, which would be much easier with high-level theorems, which we haven't covered in the material yet.
Yes, that's right, and the reason for doing that is to get you to embrace the high-level theorems by the time you get there. But the thing is, though, you do need to use these approaches sometimes. Like the high-level theorems don't always work; they just don't always apply. So you do need to use them when you can. And as I said, for A, you're just going to have to really do it. Like the boundaries, nothing need either. So you really are going to have to sort of do this sort of approach.
Yep, that's fine.
Okay. So yeah. I'm just trying to think of another way of explaining it. But in terms of this, yeah, okay, we'll leave it there. So
I would just say that, like, since in the tutorials everything's quite scaffolded out, like questions with like and so on, and given a method to use, but not like in a assignment or exam situation where you're just given an integral that was a flux integral, and there's no difference between bold A and bold S in that situation. What would be the main thing to look for, I guess, toward using the strategy that's in question 9 in front of you, compared to using the old strategy of when it was an S?
So I was going to do this. I was going to cover it next week, but essentially, I would normally go through, check for high-level theorems first. So if it's a closed surface of a flux, just use divergence theorem. That's definitely easier. If it's open surface of a curl, so you integrate doing a flux of a curl, then use Stoke's theorem. If neither of them apply, then you're gonna have to do it directly. If the unit normal is really easy to work out, well, bang, you use that, and you could try to that approach, which you can almost do in 9A here. But
because I don't actually have any access to Stokes and divergence theorem yet, because I'm still doing tutorial 9.
Yeah, so I mean, as I said, they don't apply. So, but that's what it. Yep. So in this case, you're going. Well, I'm going to have. So in this case, it's not an. It's a surface which doesn't. I mean, it's hard. I'm going to have a hard time drawing it. So therefore, I'm really just have to fall back to parameterization. That's always the default option. So as soon as I parameterize it, they're going to have to use this approach. This approach really is just the parameterization method. And this particular, as I've written, this formula I've written down the top, these two here, are parameterizing in terms of x and y's. So if you're going to parameterize in terms of x and y's, which works almost all cases, even if you've got polar coordinates, I still recommend parameterizing in terms of x's and y's. And then you just go from that. So you go, okay, I'll parameterize it. I can do one right now if you want, just show you how you do it.
Work through it, but I guess with the x, y, z parameterization, you've got that formula.
So what I mean by this is basically I get the parameter z is equal to some function of x and y's.
Yeah, but I mean that's the best option basically without using the
yes.
Right,
yeah.
That's fine.
And even with the high level theorems, you really can't. I mean, you can't do much better for some of them anyhow. Like even with them, even with your chance to access them, it doesn't really help in these cases anyhow. Like this is a bit of a parabolic cylinder. Like you're not gonna close off in any hurry. So trying to use some high level theorems is just not going to work for you. So you're going to have to do it via parameterization method anyhow. Alright, thanks for your time, guys. So I'll spend more time on flux integrals next week as well. So if you're still, so you can try ask me again next week if you need to. I can do I'll do a long example of one of those if necessary as well. I've got some I was planning to. So thanks for your time and thanks for asking tricky questions. That's exactly the idea. But see you next week. Cheers.